This is the third on the series of videos about AMR-One Project.
Hi, this is Alejandro Alonso, and today I will talk about architecting the solution. In the previous video, I described the requirements, so we know now what are the functions that the system should accomplish. But before defining the tasks to accomplish these requirements, we need to have an idea on how are we going to build a solution. For that, some people tend to create more technical requirements in the language of the developers. I prefer to spend some time working on a pre-design of the whole system, from the mechanical, electrical, and software sides, but involving representative people from each of these disciplines. It is essentially an iterative process, but having a basic architecture already opens minds to understand the tasks needed to build the system. When we have this general pre-design of the system, we could go further on classes definition for software, material for mechanics, or technologies for hardware in general. Let's see now as an example how this architecture has been defined in the AMR-One Project. The mechanical approach starts with an overall analysis of the kinematics of the needed system, then continue with some freehand sketches, and then with some draft ideas using computer tools, but not going in deep on the design. The hardware and electrical architecture defines the components, sensors and actuators, but what is more important, help to define the processing systems and the functions assigned to each of them. We define 4 processing systems: a safety PLC, a low-level controller, and a high-level controller in this hardware architecture. Also, we have a cloud-based system that is not mentioned here because it doesn't need any hardware from our side. Going a bit further on the functions assigned to each of these processing systems, the safety PLC is responsible for ensuring the safety measures are executed reliably. It uses several inputs, like the safety LiDAR information and safety stop buttons or remote stop, to determine when there is a dangerous situation, and the system then in that situation should stop, in this case the drives. There is therefore a program inside this PLC to ensure this behavior. The low-level controller is responsible for the low-level functions, which are the following: sensor reading, traction motors PID control, so here are the motors, the drives, also the velocities conversion into inputs for these PID controls, the magnetic guidance based on this sensor or RFID tag reading and execution of actions, the pin hook control that we mentioned, it is a device to hook the trolley, a buzzer control that is inside for warnings, the LCD screen, the chime, and the function of RAS publishing to communicate to the high-level controller. In version 1.0 only send information to represent that in the cloud, for monitoring. And from version 2.0 there is a bidirectional communication, publishing, subscribing through topics to communicate with the HL high-level controller that will guide the AMR, because the high-level controller is responsible, at least in version 1.0, for this communication that I mentioned, and also the communication to the cloud, mentioned, and from version 2.0 it is responsible of the communication of bidirectional and also the localization, navigation and mapping based on ROS. Now let's see the solution approach from the software side. As mentioned, there are these 4 processing systems, each of them with programs inside. So I will show you the overall software structures defined for these processing systems. In the case of the safety PLC, it is very easy. It's just to identify if there is something compromising the protective field. The protective field is this red thing, so you could define warning field with the LiDAR, and these warning fields usually are to reduce the speed of the AMR, and this protective field is that if something is detected here, the AMR should stop immediately. So it's what it says. If it is detected somewhere there, then activate the emergency stop, so it stops the drives. If not, okay, there is a safety button, emergency button pressed, yes, do the same. This is used in the case that you want the AMR to stop immediately. You could do that, or you could use a remote button for that. If nothing of that and the emergency stop was not activated or not active, then okay, it's a loop. If for any reason it is activated, the emergency stop, then whenever it is the problem is then eliminated, then it waits 3 seconds, then release the stop, so it continue moving. What happened in the case of the low-level controller? Okay, as mentioned, it has many functions, and they are represented here. I will not go much in deep on that. This yellow color is because it's for version 2 and the rest is for version 1, but basically it is this publishing part for ROS for the monitoring. Okay, this HMI update, buzzer warning module that activates the buzzer if something is wrong, the RFID module that reads the RFID tags and activate something like imagine an RFID tag saying that pin hooks should go up, then when it is red it goes up, these kind of things, or reduce the speed or whatever. And then depending on the guidance that has been activated, it could be magnetic or SLAM. In the case of magnetic, there is a module to control using the readings from the magnetic reader. It guides the AMR with the pitch control also. And in the case of version 2, it could be choosing the ROS based system, so it would use the ROS subscriber and publisher to ensure that from the high-level controller everything is controlled properly. Okay, there is a good bidirectional channel. Also, there is a safety control module that it comes signals from the safety PLC, and it says like, okay, the safety PLC could stop the drives, but also should inform this low-level controller to say, hey, don't try to move the AMR, I'm stopping that. Okay, and also some velocity updates on the motor's PID controls, taking information from encoders, sending to drives. Like quite easy, and it's a main loop here. Okay, quite straightforward. In the case of high-level controller or HLC, everything is in yellow because this is for version 2, not for version 1. So this is more, you need to understand ROS for that. Okay, if you do not understand ROS, probably it will be strange for you, but I recommend you to check about ROS. But basically it brings it launches some modules, so bringing the base, the AMR-One base, a joystick for manual control, the module that controls the LiDAR inputs. It launched a map server that basically have a map of the surroundings, so the AMR could use that map. It starts the AMCL, the adaptive Monte Carlo localization package. that is used for the system to track the localization of the robot in the 2D space. We define where exactly the AMR starts. Usually it's the charging station in the map, so we say, hey, you are here. We launched the MoveBase package that provided implementation of an action to move the base. The base is the AMR basically. We set some navigation parameters, and then we go to this iterative control module that basically is a Python program, and it basically shows at the screen some buttons on where to go. I go to this station, go to this cellar, and then reading these positions, then it just asks a button press, call action server to move to stop point assigned to the button. This is done everything for us, okay? And in the part of the cloud monitoring, basically this is the low-level controller and high-level controller, and this is this ROS publishing topics, ROS topic publishing using the ROS serial. And here in the high-level controller, just something converting to JSON messages for MQTT channel, because we will use this as a IoT device. And then as the cloud system, we will use Amazon Web Services, where we have several services offered by Amazon, like AWS IoT Core, some rules to store the information coming to the Amazon Open Search service, that is a NoSQL database, and then just getting some dashboards from the data, like hey, how many problems we found, or how many times the safety stop has been activated, or what is the speed of the AMR, how it has been changing during the last 2 hours, or things like that. So something like that. So we have been reviewing this architecting the solution part that really will help us from the mechanical, electrical, hardware, software sides to define the next steps that are the tasks. So in the next video we will go ahead with a work breakdown structure that will help us to understand how this architecture understanding will help us to define the different epics and tasks that we will have to execute during this project.
If you like this video, don't forget to like it and subscribe at the bottom of the video. Click the bell to receive notifications when new videos are published.